This is another video in the Systems and Proof module for Foundations of Computer Science. I'm going to work through another example of an inductive proof of a property of a post system. Now, obviously, there are many post systems and many properties, so to clarify a bit more, I'm looking at this particular post system, which claims to be for positive multiples of 3. And in a previous video, we used strong induction to demonstrate the soundness of that claim, right? To prove that all elements of this system are in fact positive multiples of 3. So in this video, we're going to prove the completeness of the claim, which is to say that all positive multiples of 3 actually are in the system. To make this claim, we're going to use weak induction. And so I think from the outset, it's probably worth spending a moment or two discussing why it is that we're going to use weak induction this time when we used strong induction to prove soundness. And the reason has to do with the way our sets are defined. So remember, this was our post system that defined our set that we were trying to prove soundness over, right? And what we mean by soundness is we were saying that anything in this set is in fact a positive multiple of 3. That means we wanted to start with things in the set and go from this set to the set of positive multiples of 3. And in order to make sure that our proof really did apply to every element in this system on the left, we had to write the proof in such a way that took into account the way the definition is set up. In particular, we had to recognize that there was a possibility that x and y might have different derivation heights, and that's why we needed strong induction. We didn't quite know what their derivation heights would be. We did know that if the derivation height of our bottom element was k plus 1, that the derivation height of the antecedents has to be less than or equal to k. Now that we're proving completeness, however, it's reasonable to think of us as changing the direction of the proof, which is to say we're starting with the positive multiples of 3 and trying to prove that each of these positive multiples is in the post system that we defined. And since that is our approach, it means that our proof strategy fundamentally depends on the way that we've defined or are going to define this set on the right. So the next logical question is, what is that definition? Remember, a number is a positive multiple of 3 if it can be written as 3 times some other number when that number itself is a positive integer, right? So we'll say n is a positive multiple of 3 if it can be expressed as 3 times k, where k is some positive integer. So that definition is pretty straightforward, and you've probably seen it before, but a direct implication that is an important thing to recognize is that if we want to generate all positive multiples of 3, we can do it just by checking all of our k values. And that means starting at the first k value, which is 1, and then just repeatedly adding 1 to get all of the rest of them. So the key takeaway here is that k would make a very good parameter to do induction over, and what we'll see as we work through the proof is that you really never have to look back more than one step at a time, and ultimately that is the reason that this will end up being a proof by weak induction. Okay, so that is probably enough preliminary discussion. Let's move on to setting up the proof. So first, we'll leave ourselves just a reminder of the definition of a positive multiple of 3 and a note that we can always express these as 3k for some positive integer k. Then, just to be extremely clear, I'm going to state explicitly that the method I'm going to use is to prove by weak induction on k that 3k is in the set M. Now, just a small notational nuance here. I've written that k is an element of the natural numbers. Sometimes the natural numbers are defined as including 0, and sometimes they are not. For our purposes here, we are assuming they do not include zeros. In other words, this is equivalent to z plus, right? And it might have been actually better to write z plus and avoid ambiguity, but at any rate, hopefully it is now clear. Now, the next step is to rewrite this claim we're trying to prove as some s of k, where s of k is a statement that is parameterized on this k. And so what we get when we do that is we say if k is a positive integer such that k is greater than or equal to 1, then 3k is in M. And note again, like in the previous example we did with strong induction, when we change to this parameterized version, we're really not changing the meaning at all, right? Our original here, in fact, looks very similar. And the only difference is we've said if k is a positive integer such that k is greater than or equal to 1. And that is true for all positive integers, right? So it does not really change the meaning, but it will help us hopefully organize our inductive proof. All right, so now that we have an S of k, we can write out the full outline of our inductive argument in terms of S, right? So we start with our base case here, that's S of 1, and then we say for all k greater than or equal to 1, if S of k holds, then S of k plus 1 holds. And if we manage to establish this, then our conclusion is established, and our conclusion is that for all k greater than or equal to 1, S of k holds, which is the same as saying S of k holds for all positive integers. And this would prove completeness. And just to restate this symbolic, sort of dense form of the proof in more of a natural language, we can write out that we're going to start with the basis, and that's where we show the statement is true for 1, S of 1. Then we'll move on to assume our inductive hypothesis. We assume S of k is true for all k greater than or equal to 1, right? Greater than or equal to the base case. And then we have to show that our inductive step holds based on that assumption. So that's the outline of the proof. So now that everything is set up, all that remains is to go through and check that our basis and our inductive step are actually true, that we can prove them. So as usual, we'll start with the basis. And in the basis case, we have S of 1, and that means that our k is equal to 1. So remember, our question is 3k in the set M, right? And so when k is equal to 1, say that's a question, right? We haven't proved that. We're trying to get there. Well, if k is equal to 1, then 3k is just equal to 3. And so by our axiom from our post system, we know that 3 is in this set. So certainly 3k is in M because 3k is equal to 3 when k is equal to 1. So that is established. Now all we have left to do is the inductive step, and once we write this out, it's also not too tricky, right? S of k plus 1, we can translate into the statement that we must show that 3 times k plus 1 is in M for k greater than or equal to 1. So we can just do some arithmetic here and say, well, 3 times k plus 1 is equal to 3k plus 3. And a nice thing here is now we've translated this expression into a form where we can more easily apply our inductive hypothesis. Because remember, we are allowed to assume that the statement S of k is true, and that means that by assumption, 3k is in the set M. So now we've established that 3k is in M, and we also know that by our axiom that 3 is in M. So both of these components of this expression are in M. And so we can use our rule R from the post system to say, well, if 3k is in M and 3 is in M, now we can produce 3k plus 3, and that must be in M. Now, we're almost at the very end, but just to make sure we don't lose anybody on this last step, remember that rule R states just that if x is in M and y is in M, then x plus y is in M. And so all we're doing here is taking 3k as our x and 3 as our y, and concluding that indeed we can now produce 3k plus 3, and that is in our set. And so then in our final step, we simply factor out the 3, and we end up with 3 times k plus 1 is in the set M. And this matches the form we set out to show, so we have completed the inductive step and completed our proof of completeness by weak induction.